Hi there and welcome from Ventura, California to today's webinar, Case Studies in GNSS INS Integration, sponsored by Novotel and Inside GNSS and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address two very different engineering challenges: high dynamic platforms and car navigation, that require very different answers but are arrived at through similar design methodology. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation today during the Ask the Experts panel session with both of our panelists. Now, we've invited you, along with over 500 professionals registered from 43 countries and 30 states and provinces, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Glenn Gibbons, editor and publisher at Inside GNSS, would like to take a moment to welcome you and introduce our sponsor as well as our main moderator for today. Over to you, Glenn.
Thank you, Lori. And on behalf of the Inside GNSS team, including our Director of Business Development, Richard Fisher, and myself, I extend a hearty welcome to our international audience for today's web seminar. In just a few minutes, we're going to hear some fascinating descriptions of the integration of GNSS and inertial technologies for use on aircraft and land vehicles. Before we get to our speakers, however, I would like to introduce Sheena Dixon, representing our sponsor for today's webinar, Novotel Incorporated. Welcome, Sheena.
Hello, everyone, and welcome to the GNSS INS Integration webinar. We at Novotel are extremely happy to sponsor this event. As one of the pioneers and industry leaders in GNSS INS technology, we're excited to hear what our presenters have to say today. I will be back during the Q&A sessions and will be available for any questions you may have. Thank you and enjoy the webinar. Back to you, Glenn.
Thank you, Sheena. And now it's time to turn the webinar over to our moderator, Demos Gebra-Egziaber. Over the years, Demos has helped develop and moderate numerous Inside GNSS webinars. In his day job, Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota Twin Cities campus. Demos, thank you for joining us again for today's event.
Thank you, Glenn, and glad all of you could join us today for this fascinating webinar this afternoon. As we normally do, before we get started, let's do a quick poll. So, Lori, if you could cue up the poll.
I would be happy to. And coming up on your screen is that first poll, and we'd like to hear from each of you. Which of the following are true of design requirements for an integrated GNSS INS system? So for a given hardware, GPS receiver and MIU are independent of the application. For a given application, are independent of the hardware used, are cast in stone and never change once the design process starts, may be determined iteratively as the design process evolves, or perhaps all are true. Go ahead and let us know what you're thinking. So we've got 20% for a given hardware are independent of the application, 15% for a given application are independent of the hardware used, 2% saying are cast in stone, 62% say may be determined iteratively as the design process evolves, and 25% weighing in with all are true. So Demos, any thoughts here?
Well, that poll question was kind of a trick question, and it's motivated by a question or comment I've heard many times. So moving on to the reason for us putting that poll question together is, again, the question's been asked a lot of times is, why are there many different types of INS GNSS integration? Doesn't one of them work for all particular applications? And I think part of the problem why that question comes up is because we present the INS GNSS integration as shown on this slide here, where we have a block for the INS, a block for the GNSS, and some sort of a filter that blends them together. And it almost always looks the same. Sometimes there might be a slight variation where we have like deep integration where the GNSS receiver is being aided by the filter outputs. But again, this kind of leads to the impression that all integration strategies are more or less the same for different applications. The fact of the matter, they aren't. And what we're going to do in today's webinar is actually walk you through 2 case studies where you'll get to see the beginning to end process of designing an INS GNSS system. And you will get to see how the design requirements evolve and how are they different for different applications. The first one will be a GNSS integrated with a tactical grade inertial sensor for a high dynamic application. And the second one is going to be a GNSS integrated with a consumer or automotive grade or low quality inertial sensor. And as we go through this webinar, basically what I guess we hope you see and get out of this is understand how are the design and integration architectures and the design process is different for the different types of sensors used and different types of applications. With that, I will go ahead and introduce our first panelist, who is Thomas Jekyll, who is a senior engineer in Honeywell's Sensing, Guidance, and Navigation Center of Excellence. He holds a BS and an MS degrees in aerospace engineering and mechanics from the University of Minnesota. Tom Jekyll's research interests focus lie in the area of inertial navigation, GNSS inertial fusion, and MEMS inertial sensor design for navigation applications. He has been involved in a wide range of navigation programs within Honeywell, from deeply integrated tactical navigation systems to safety critical GPS landing systems. With that, Tom, I'll hand it over to you.
Thank you, Demos. Today it's my pleasure to discuss modular system design for a range of high dynamic applications. So the goal is to produce an integrated inertial navigation system architecture which is adaptable to various high dynamic environments, minimizes the free inertial drift during GPS outages, and is configurable to use various inertial measurement units and GNSS types. And I'll talk about a particular example of this. And so in the picture here, if you have a GNSS or GPS antenna on the top of the aircraft, you are currently experiencing an outage or most of your satellites are blocked. So in this talk, I'll be discussing cases where we want to hold our navigation quality through outages like this. So as indicated in the poll question by the majority of users, you can see that we have an iterative process here. So our goal is to define the dynamics and requirements, perform a system design, followed by an algorithm design, simulation, evaluation, and then feedback. And this feedback is especially important in designing navigation systems for high dynamic applications, since the performance is dependent on the actual dynamics involved. And I'll show that with a simple example for the inertial sensor selected for this design. So first step, define your dynamics. So you want to pick a representative trajectory or several representative trajectories, figure out the inertial forces, and since the example I'm talking about today is confined to strap-down navigation, it means sensors experience the full motion of the body with some attenuation due to how they're mounted, say by an isolator or otherwise, which is different than gimbaled navigation where the body is free to move. And I'll talk about strap-down navigation specific force modeling fidelity. It's critical for navigation applications, but as you'll see in my error models, not so much in tactical, although it is something we still do consider. And since it's a high dynamic application, we also have to look at mechanizing the equations to include the transport rate since you're moving quickly. And other things to consider are high frequency dynamics such as vibration and shock. And those are considered high dynamics, and they do put the system under a certain amount of stress. So there are certainly requirements around surviving those. So requirements, size, weight, power, and cost. In a lot of aerospace applications, size and weight are really key because they cause other parts of the system to have to cut weight, and you're trying to lift them up high, fast, far. So power can also be a constraint, and cost, generally not as much, but still an important consideration, especially with today's budget constraints that are going on. And of course, given it's a high dynamic application, you want the dynamic range and bandwidth driven by your platform dynamics. So after you figure out your trajectories, you don't want to have the sensors not measuring the full bandwidth or the full dynamic range. So those are key requirements. And then for performance, generally you first start off with navigation performance or something that's a little bit more easily quantifiable, and then work that. The arrows will be the focus of the first part of my talk. Work that into what are your actual inertial performance requirements and your measurement performance requirements from given your trajectory and some tools that I'll discuss. And then of course there's always other considerations: reliability, technology readiness, and ease of adoption. So after you define the requirements, kind of for your system design, you want to look at a list of candidate IMUs. So you know that you have outages and severe dynamics which require inertial technology to track those. And so you have a list here of Honeywell IMUs, and this is driven by, for us, a requirement that we have an ease of working with the factory and all parts of the process. So you have from smallest to largest Honeywell tactical navigation IMUs, and you can see the volumes here in cubic inches, ARWs, and other performance parameters. And some of the key parameters I'll be talking about are scale factors, and I'll focus more in on that with the IMU selected, the HG 1930, which is a Honeywell tactical IMU. Well, okay. So now I'll talk about the IMU selection. So in our case, the design is driven by the volume. We want a small volume device, so less than 5 cubic inches, that weighs less than half a pound and draws less than 5 watts of current. So the 1930 fits into that. It's been adapted for guidance, navigation, and control applications on both commercial and military platforms, and it offers extended range versions, so the dynamic range can go over these values shown here. And in addition, there will be a non-commerce controlled version coming out in 2016. So as far as being deployable across broad markets and in space confined environments, this is the IMU that we selected. And then there's a variety of performance. So there's 3 performance families available, and you can see the different performance characteristics. And I'll discuss why you pick a certain one and what the impact would be on performance depending on your common filter selection parameters. So now I'll talk about, we kind of have an idea of what the INS, an IMU will be using for our INS, and I'll talk about the navigation algorithm design. That is, how do we incorporate this in a navigation solution? So our navigation architecture is centered around strap-down navigation and an extended common filter, and it's been proven, and this architecture has proven navigation performance in past environments. And for GNSS inertial integration, we select the psi-air model so we can directly observe the Earth-to-body states and model the inertial sensor and measurement errors, and I'll go into that in more details in the coming slides. And note that the dynamics of these states, the observation of these states, is heavily dependent on the trajectories they're experiencing. And we also want to have a selectable navigation iteration frequency to so you can model certain parameters at different rates depending on other computational loading on the processor. And for high dynamic environments, incorporate GNSS measurements with ultra tightly coupled navigation solution or navigation incorporation. So we bring in the measurements and with feedback through the NCO commands to actually drive the GPS receiver replicas, and that's primarily there so we only have to track the error in the INS indicated dynamics and changes in the receiver clock dynamics instead of tracking all the dynamics. So you're just looking at the errors when you're driving. When you're doing that, you don't have to be concerned about the actual dynamics being experienced by your high dynamic platform. So now we'll talk about one of the drawbacks of deeply integrated or ultra tightly coupled that can be overcome with a specific receiver design. So these are really requirements around a receiver used for this type of application. So it has to be able to accept NCO commands from external sources, output I's and Q's at 50 hertz or greater, and that is for signals with navigation data on them. Newer signals are coming online without nav data that should relax this requirement. And the bias estimation and whatever corrections are made in the GNSS receiver should be consistent with what's going on in the common filter, since when you go with a DI or UTC application, you're running, you combine everything into one filter, and any other things done in the receiver should be known in the central processor. Another requirement for us is a small size, weight, and power. If we selected the small IMU and then put on a huge GPS receiver, that's going to be an issue. It kind of negated our reason for selection in the first place. And then the next requirement is oscillator stability under dynamic conditions. So the oscillator G sensitivity should be at least consistent so that it can be estimated. As I mentioned before, the receiver only needs to track errors in the inertial solution and, of course, its own clock. And the signal acquisition time may be critical or may not be critical, and I'll discuss that later with some performance results. And that really depends on your requirements post initialization. So now I'll talk about, we have the INS, we have the GPS now, and we have the mechanization to bring them together. Now, specifics of how you select certain states in your extended common filter. People generally use a covariance or a time domain simulation, and initially, before we really know what the algorithm design is going to be, start off with a covariance simulation. That is, you have linear models of error characteristics and a single run statistical assessment, as compared to a time domain simulation where you are simulating your full algorithm, you're running it through, say, a Monte Carlo analysis and getting a statistical assessment, which takes longer for a given extended common filter design. So the first thing we generally do is covariance analysis. So what you see here is you have measurement errors modeled here. As I showed in the beginning, you have some trajectory or mission profile. You have your navigation error model, which is your mechanization equations, your sensor error models, and this is the full set of sensor errors that you want to put on that. And of course, that's really critical because your results are only as good as your inputs for your simulation, as good as they match the actual environment. And so what you do is a covariance analysis, and really what you're getting out of this is the difference between a really high order filter with everything that you think should be included in the error model and candidate filters. So you're trying to select states that are going to be both observable and with your measurements and observable by your dynamics. So now I'll take you into for a high dynamic environment, say an example of estimating a state. So the gyroscope scale factor is a common state that needs to be estimated in these high dynamic environments, and I'm going to visit the case where you do a 180-degree roll, like that aircraft rolling over on the introductory slide. So if there's no state in the extended common filter, and you have a scale factor from our specification of 1,000 ppm for the AA50. So if we go back up for our HG 1930 AA50, you'll see that the scale factor repeatability is 1 sigma is 1,000 ppm. Then you're going to get an attitude error for that roll of 0.18 degrees because you've rolled over 180 degrees, and you have this error in parts that brings that attitude, that causes that attitude error. Now, because of that, you're going to misresolve velocity for dead reckoning, so you're going to get this much error in your solution. Now let's say you've estimated the state in your extended common filter, and generally you can estimate to a little bit better than the in-run stability depending on dynamics. So you can estimate to the in-run from the AA50 spec, and the in-run is 250 ppm, so your attitude error becomes 0.05 degrees, and your misresolution of velocity for your dead reckoning becomes much, much smaller. So modeling that error really provides performance benefit when you are going to do these maneuvers consistently. And of note is you have to have the trajectory to allow it and the measurements to allow it. So now I'm going to cover some more available states. Obviously, inertial states, you can model the bias of the sensors, the scale factor, as I just mentioned, any scale factor nonlinearity that's repeatable for the sensor, misalignment, non-orthogonality, and gyroscope G sensitivity, and some GNSS measurement states, clock drift rate, range bias, and oscillator G sensitivity. And of course, these states have to be repeatable and modeled as close to the real system as possible. So, but another thing to keep in mind is your state selection is a trade-off between performance and processing. So if you have too small of a processor and you can't extend your Kalman filter far enough before you run out of processing power, you may have to remove some states, and you want to do that in accordance with what your covariance analysis says is the state that impacts your required performance as little as possible. So now I'll talk about test environments. I showed some examples of offline simulation tools, just what can we do offline to analyze the performance, then laboratory tests, which includes vibration testing, hardware-in-the-loop testing, exposures to controlled environments for your requirements, and our development utilized all these above environments, and then kind of after you check out the device, you go on to van testing for low dynamic motion to check for visibility into timing errors. And it's generally cheaper than flight tests. You can put a lot more instrumentation in your van. We actually use the Novotel Inertial Explorer software to run our test IMU through, and it's nice because it allows us flexibility of IMU inputs, so we can take our unit under test, run it through that software, compare it to our solution, take our reference unit, which is a custom-built Honeywell navigation grade IMU, put it through that software, and then compare it to our navigation solution. And even though it's a lower dynamic environment, you can certainly see things like lever arm errors, problems with timing, misalignments between systems. So that's good to check out before we get into the flight test. And of course, we get into a flight test, the reason you've designed your system so small is it's space constrained for these types of the actual environment will be in. So adding any other instrumentation takes money and time, so it's good if you've checked it out in the van test ahead of time. Then you take all that information you've learned from these tests and feed it back into your offline simulation tools to make a more complete model of your system. And so I talked about the process, and now we'll talk about kind of the outcome of our design, and it's the HG1930N integrated navigator product. You can see it has the same form factor as a 1930. You can see it compared to a quarter here, and it's a drop-in replacement for any 1930 that exists. And the key here is flexible I/O options. So I talked about UTC and the need for, feedback to the GPS receiver. So this has low latency ports. It's also capable of handling external IMUs. So if you had a system, if we get a system in that needs more performance, we can design to that. So what you can see in the system is the Honeywell IMU software, all the calibration, all the stuff necessary to get it to those performance requirements is running on one of the processors. Then optionally you have the Honeywell navigation software, or it could be an external software, and it's in an open environment, and you can see it's communicating with UARTs, SDLC, and external I/O. That'll show on the next slide. So it's a 14-pin connector, and it's compatible with existing for volume, commonality, production, and cost. And so that has limitations because it's only 14 pins. There's certain systems that you want more pins to get more measurement sources. I mean, Doppler, stuff that I showed on the previous slides. So it has these ports that are configurable and capable of changing. For legacy programs, it has an SDLC port, and pin options to go to different time mark ins and outs to support different GPS receiver implementations. And so there's just various navigation usage you can use with this. So that gives us the flexibility that I talked about in the goals. Now, system performance. So we went through the whole design, went through all the testing, and then fed it back into our simulation. So what you can see here is navigation performance is similar to the Honeywell BG1930, and I'll refer you to a reference at the end of my presentation. And so we initialize it with a certain amount of error, and we want to see that the transfer alignment measurements incorporated into the common filter do their job and take it down to close to GPS level accuracy. Obviously, so this is the application is a UAS glider out on the wing of an aircraft that's being transfer aligned. So you have a master navigator that's providing position, velocity, and attitude updates, but you have the flexure of the wing relative to the internal bay, and then at some point the glider is going to get launched. So you have a launch phase, and so for two different GPS receivers with a different time to first fix, you have different performance. So for the 20-second time to first fix, there's this performance. You coast free inertially there, and then at some point it recovers. And then you have a lower time to first fix, and of course this is the GPS receiver being unaided generally has closer to this, and aided is closer to this. And then you have some period where the unit is running with GPS measurements incorporated, and at some point you go free inertial. And so after 1 minute free inertial performance, you have 18 meters of CEP and 12 meters of altitude error, 1 sigma. So CEP is just think half the time it will go over that, half the time it will go under that error amount, and then attitude error is 1 sigma. So future developments, I won't spend too much time on that. We just have additional options to configure, put in a different GPSR, swap out other aiding sensors, do USB on the go, which means you can just plug it into a laptop. This concept is also being defined for other Honeywell product families, so this all supports a very configurable, flexible architecture. So really what I want you to take away from this presentation is that when you go to design a system for a dynamic environment, it's an iterative process, that you have this trajectory dependence that you have to constantly work out and consider. And high-fidelity simulations provide a low-cost means to iterate on the design. So anytime you go back and you change requirements, you can hopefully, if your simulation is good enough, and we've proven in a number of cases that it is for certain requirements, you can go and simulate instead of having to go out and redo some of those costly man and flight tests. And really modeling and knowing the sensors and understanding how they perform under dynamics is critical, because if your model doesn't match, your simulations won't match, and you won't be able to do that mapping that I talked about between your desired performance requirements and the inertial performance requirements needed. I saw a lot of questions where what is ultra tightly coupling and how does it impact things? And one thing that should really be noted is that selection of ultra tightly coupled has a significant design impact when you're talking about GPS receivers or GNSS receivers, that the receiver has, your receiver and your inertial unit is effectively become one, and there has to be significant communication and design modifications to the receiver to incorporate that. So here's some references. So for deep integration, I really like this paper by Paul Groves, and for more performance results on the BG1930, here's another paper. So, all right, thank you very much, and I'll turn it back over to demos, and I look forward to answering your questions.
All right, thank you very much, Tom. So at this point, we will take a pause and start entertaining questions from the audience for both of our panelists. So let's go ahead and do that. So let's see here. So the first question is going to be for our second panelist, even though I haven't introduced him. I'll introduce him in a bit. It's Andre. And the question is, in a INS GPS integration that uses a Doppler-derived velocity and carrier-smooth pseudo-range measurements as aiding, the measurements are correlated. Any thoughts on how you deal with this? I know that you'll talk about this in the second half of this webinar on your presentation, but if you could go ahead and address that question from one of our audience.
Sure. So there may be two aspects of this question. First of all, you can have measurements correlated with each other. So if you, specifically if you're talking about position solution, then because position is computed from pseudo ranges, then position errors in east, north, and up components can be correlated with each other. So this is a relatively straightforward thing to address. You just directly incorporate it into your measurement covariance matrix. This correlation mechanism, just put it in there. Another aspect, which is not so evident maybe, is how do you address it, is when the measurements are correlated over time. So to me, probably the best approach to deal with it, you just include bias states into your common filter to address this correlation. In other words, you include the error, the correlated error over time as an additional state in the filter. And the filter is probably due to observability issues. It won't be able to estimate this error, but it will be able to model your error states correctly and address this correlation mechanism.
All right. Thank you, Andre. And I'm pretty sure you're going to say more about that in the second half of the webinar. So whoever asked that question, stand by. Next question. This one is going to be for you, Tom. And I guess there was a question about, you used a term covariance simulation when you're describing your design. What exactly is that? Can you explain it a little bit more?
Sure. So covariance simulation is really a means of taking the potential errors in an inertial system and bringing them into the physical position, velocity, attitude domain. So what you're doing is you have a extended Kalman filter that's tracking all the states with the covariance as the actual error and saying what is the error budget for position associated with gyro bias or gyro scale factor. So it's a way to map those things. So you're actually linearizing about a model similar to actually exactly what you do in an extended Kalman filter, and putting the covariance in as error for that simulation and determining what the outcome is, and then you're comparing. Say I have this and I turn this on or I turn it off. How much measurement error am I going to move or remove by having this on versus off? So for certain trajectories, some states won't, or some error sources won't lead to much error. For others, they'll lead to significant error. So that's all covariance simulation is meant to do.
All right, thanks, Tom. Let's see, next question. This one, I guess we'll go for Sheena, for our sponsor from Novotel. Obviously, when Tom made the presentation, it's clear that it takes a lot of experience and expertise for someone to put together an INS GNSS integration. For those just starting out, are they out of luck and have to really wait on the Honeywells and others to do that integration, or is there products or support that they can get from someone like Novotel in helping them start up designing INS GNSS systems?
Yeah, absolutely. I mean, putting the two pieces together, it's definitely not easy. We do have our SPAN Inertial GNSS product line, so we've done all of the integration for our customers. So everything that Tom talked about, it's all done on board on the receiver side. So everything runs on the receiver with an ultra-tightly coupled integration between the GNSS receiver and the inertial sensor. So you can buy the separate pieces directly from Novotel, put that into your system, and everything's good to go. So we've done all the hard work for our customers.
All right, thank you. Let's see here. Next question. Let's see. I'll address this one to Andre. And actually, after Andre answers, probably Tom can chime in too. And the question is, how important is numerical accuracy or precision when you're implementing these inertial navigation equations with an INS GNSS integration?
All right, the answer is it really depends on the application. If you're talking about high dynamic application, with precise sensors, then it's important. You want to take care of your Conin effects, scaling effects, maybe, especially if you're dealing with high vibration scenarios. For lower grade sensors, and I'll address it in my talk a little bit more, the numeric precision is not that critical because the sensor errors, gyro biases, and accelerometer bias is going to be completely overshooting your numeric precision. So you don't really need to spend a lot of effort there. But I'll talk a little bit more about it. But the answer is it really depends on the application, and you really need to see how your numeric precision errors contribute into the overall error budget.
Anything you want to add to that, Tom?
Well, sometimes, so I agree with Andre that it can be important for critical applications. In regards to, say, directly precision errors like quantization, it depends on the averaging time that you're looking over. So if you care about high dynamics and tracking in really high bandwidths, then it's a big deal because the bit, your errors obscure the area that you're looking at. But if you're actually looking at navigation performance on the order of 1 second, then you at least have some time to average those out. So again, it depends on your errors. For things like pointing, where you want to point at for a high dynamic application, it's critical to get rid of and resolve those errors. But for other applications, it may not be so critical.
All right, so let's see, one more question before we have to go off to the second half of the talk. We're getting a lot of questions. Thank you for the audience, and keep them coming, and we'll try to address them on the second Q&A at the end of the talk, at the webinar. So the next question, I'll start with you, Tom, and it has to do with vibration. And how do you take that into account? I mean, could you consider vibration the equivalent of a high dynamic environment, or is it handled separately?
I would consider it a high dynamic environment, and one of the things that Andre mentioned that you have to test is your coning and sculling algorithms. You want to ensure that they're high enough order and that they feed into the error budget you're expecting. So that's really critical. And so if you're taking and you have your IMU sampled at one rate and you want to go to a lower rate before you actually perform the mechanization, and you have some algorithms, you really can test those offline. The good part is that can be done in the lab. It doesn't have to be done on the platform. You can kind of have a feedback. What you measure in your platform can be fed back into your lab environment, and there's ways of doing that. So you can test it in your lab, and then you can characterize that. You can bring it into your simulation and test your algorithms that way. So yes, it's a very important consideration.
And is it? I take it it's part of the covariance analysis that's done, or is it handled the same way, or is it handled differently, or can you say?
It's handled differently because the covariance analysis simply deals with how your extended Kalman filter estimates certain states. There's the certain states that's done at a much higher rate, so you generally can't really remove that effect in covariance unless there's some predictable error that happens every time at a certain vibration, but generally those are fairly non-predictable depending on your sensors.
All right, so for the sake of time, let's stop the Q&A at least for now at this point. We'll pick it up later on. So let's go to the second half of the webinar, and let me introduce our second presenter. But before we do that, let's take a quick poll. Lori, if you could put a second poll question up.
Sure. And on your screen, you should see that second poll. And the question is, which of the following are true about the INS mechanization used in an integrated GNSS INS system? So this is the same for a given application regardless of the quality of the IMU used. Same for a given quality IMU regardless of the application used. Always the same for a given quality IMU and GNSS receiver. Depends on the customer requirements, or none are true. And it looks like 8% say same for a given app regardless of the quality of IMU used, 17% weighing in with same for a given quality IMU regardless of the app used, 13% always the same for a given quality IMU and GNSS receiver. I think the front runner here is 72% saying depends on the customer requirements, and 8% weighing in with none or true. Demos, any thoughts here?
72% say depends on customer requirements. So I guess must have a lot of people in the audience that design for customers and tailor their INS GNSS design for customer requirements. However, as you're going to see on the second half of the talk, that's partly true, but also it depends on the application. So if we could move on to the next slide, where I'll introduce our next panelist. Andre is going to present on GNSS inertial integration for land vehicles, where you'll get to see that the mechanization equations depend on the type of application. But let Andre present that. But before he does, let me introduce him. Andre is the president of QNAV, an R&D business enterprise. Previously, he served as a senior research engineer at the Ohio University Avionics Engineering Center. He has authored and co-authored more than 80 navigation-related publications, and his research interests lie in the area of sensor fusion and signal processing for navigation. So with that, Andre, I'll hand it over to you.
Well, thank you, Demos. So I'll be talking about a second case study, and in my case, we're looking at the land vehicles and land applications. So significantly, as compared to the case study that Tom considered, the dynamics is significantly lower, but we also have to deal with much lower quality sensors on the inertial side. So let me switch to the next slide. So just before we're going to start and talk about the system design and how we actually design the integrated system for land applications and specifically automotive applications, let me just introduce a few applications what we're interested in. The first one is navigation, and it's really using the navigation for your navigation displays to get you from point A to point B. In this case, we're really interested in a road level type of accuracy. The system just got to put you on the right road, and then the mapping component and the road planning component will do the rest for you. The second application is probably not as well known, but it's very interesting in my mind. It's automotive safety with connected cars. So I'll spend a few minutes on the next slide to describe this application, a little bit more details, but the main idea there, your cars, they extend navigation-related information, position, and velocity to prevent accidents, even for those cases where there's no direct visibility, when one car cannot necessarily see the other. In this case, the lane level of accuracy is required. And the third example here, self-driving cars. Google gave a lot of publicity to this application, but other automotive manufacturers are working on this domain as well. In this case, the accuracy requirements become quite a bit more stringent, and they really want to have decimeter level of positioning accuracy to enable self-driving applications. So connected cars is something probably what will take place before self-driving cars. So it's based on the communication, vehicle-to-vehicle communication, or V2V, between two cars. They really exchange the navigation information, position and velocity, to see if there are two vehicles on the collision course and warn drivers if that's the case. So it's not an automated system per se. The driver is still ultimately responsible for the final action, but the system is much more efficient as compared to some of the existing safety systems, for example, blind spot warnings and things like that. So it really enables you to see around the corner by, again, exchanging the navigation information between two vehicles. And there are a couple of examples on this slide here where that system would be helpful. For example, you want to take a left turn on the intersection, there's a semi-track, or even just another car blocking your view, and you cannot see an oncoming traffic. So that system, the connected cars V2V-based system, would predict the accident and would warn you so you don't make this unsafe maneuver here. The requirement here is a lane level of accuracy. And as we all probably know, GNSS is a very useful system when it comes to open areas, can really provide you this desired accuracy level. But when we go into more dense urban environments, downtown type of environment, then the GNSS becomes unreliable. Integration of GNSS with Inertial is a potential solution. However, for this application, we really have to deal with very stringent cost limitations. So we really have to use very low cost sensors. consumer-grade inertial sensors. So here are the typical performance specs for this type of sensors. It's 0.1 degrees per second gyro drift or 360 degrees per hour, as compared to the sensor quality what Tom was talking, about 1 degree per hour. Here we have to deal with sensors that are accurate at a level of 100 degrees per hour. Accelerometer bias is also not very good. It's 0.1 meters per second squared. So much lower quality inertial sensors we have to deal with, again, as compared to tactical grade inertial sensors. So as a result, actually, some things are getting easier in the system design. Specifically, strap-down navigation mechanization is easier because non-inertial effects and high-precision gravitational models, they don't have to be considered. Your sensor errors are significantly larger than those effects. So they really become second order. You really don't really have to worry about them. And I'll give you an example on the next slide why you don't really have to worry about non-inertial effects. Inertial error model is also easier. You really have to consider high order terms, or you don't have to consider high order terms such as cross-axis sensitivity because they don't really contribute much into the overall error budget. So you can include them into your model and include them into your common filter design, but they're not really going to buy you all that much. So in this case, it just makes sense to use a simpler model. But the role of aiding data becomes much more critical because inertial cannot really operate in a standalone mode for very long. So you really have to bring the aiding data in a very careful and very well thought way. So we'll talk about how you bring in the aiding data, and maybe you also have to use other sensors other than GNSS. So in terms of navigation mechanization for low-grade inertial, again, it does become easier. You don't really have to implement the full-blown inertial mechanization with non-inertial effects such as compensating for transport rate, earth rate, compensating for local gravity, Conning errors, scaling errors, then taking into account high-precision gravitational models. You don't really have to do that. So here's a couple of examples on these slides why it's not important. So I put a typical example for the transport rate, and the transport rate is really change in the orientation of your local level navigation system due to the fact that the vehicle moves around the surface of the Earth. So the typical velocity when you're driving on a highway, I can assume you're obeying the speed limits, is 60 miles per hour or 27 meters per second. And that converts into the transport rate of 1 degree per hour. Your gyro bias is 300 degrees per hour. So yeah, sure, you can incorporate this transport rate compensation into your navigation mechanization, but it's not really going to buy you anything because you really have the gyro bias of 300 degrees per hour. If you improve your performance by 1 degree per hour, you really have very, very marginal improvement in the overall system performance. Earth rate, sort of similar. Earth rate is 15 degrees per hour as compared to 300 degree per hour gyro drift. It's not really worth to take it into account in your inertial mechanization algorithms. And this simplifies significantly the strap-down INS mechanization. So this is the typical strap-down INS mechanization that can be used with lower quality inertial sensors. So you have accelerometers, they measure specific forces. You need to transform those specific forces from the body frame of reference into the navigation frame of reference using the attitude information, which is derived from your gyroscopes. Once you do the coordinate transformation, you need to compensate for gravity. And really, for low quality inertial sensors, the simplest gravitational model, assuming that the gravity point is strictly downward, the absolute value is 9.8 meters per second, is going to be sufficient. You don't really have to use higher order gravitational models. Again, because your accelerometer bias is fairly large, it's going to overshoot this high precision gravitational model if you use it. So it's not really going to buy you anything. Once you transformed your acceleration from the body frame into the nav frame, compensated for the gravity, you do one integration into velocity based on initial conditions for this integration, and you do the second integration and you get your position output. One of the questions for low-grade, low-cost inertial sensors is if you cannot measure the earth rate, how do you actually do the initial alignment of the system? Because the general approach for the initial alignment, you have two vectors. You need to know at least two vectors, non-collinear vectors, in the body frame and the navigation frame, and then you can align the angular orientation of the two systems relative to one another. So traditionally, you measure gravity with accelerometers and earth rate with your gyros, and you do the initial alignment. With the low-cost sensors, you don't have this luxury of measuring the earth rate based on gyro outputs. So you need to come up with a second vector. For car navigation, this is relatively easy. So you just use velocity vector. You can measure it in the navigation frame of reference using GNSS, and you can assume that your velocity vector in the body frame of reference is aligned with the forward axis of your vehicle, of your car. So you have two vectors. Gravity, you can always measure it even with the lowest quality of accelerometers, and you have velocity vector. You measure it based on the GNSS in the navigation frame of reference, and then you assume that your velocity, your cars moves forward. So your velocity vector is aligned with the forward axis of the body frame of reference. So you have these two vectors, and you can follow the same general approach for the initial attitude alignment as compared to the case of the more traditional inertial systems. So as I said before, the navigation mechanization in this case becomes significantly easier, but the role of aiding sensors is much more critical as compared to the case of higher grade inertial systems. And this is why. This is an example of this slide of a consumer grade INS and the position error drift after just 1 minute of standalone inertial operation. And this is only the contribution of the gyro drift into the overall position error. So you basically have about 7 kilometers of drift after 1 minute of standalone operation. Tom was showing you figures with 12 meters after 1 minute. Here we're looking at 7 kilometers. So you can't really coast based on the standalone inertial in this case. And you need efficient augmentation with other sensors, including GNSS, but not necessarily limited to GNSS. When we're talking about the GNSS inertial integration, what's the right integration mode? And there are generally 3 integration modes, and it's generally accepted and understood that there's a loose integration, tight integration, and deep integration. So really what the loose integration does, it fuses measurements from GNSS and inertial at the solution level. So if you have a solution from your GNSS, great. You can use it to reduce drift and your inertial navigation outputs and make sure the INS doesn't drift all that much. But if you don't have the solution, you have a problem. You basically go into the coasting mode. You coast on your inertial. And as we saw on the previous slide, you can't really do it for a very long period of time. The tight integration is fusion of navigation measurements. Even though you may not have enough measurements to produce your GNSS position fix, the tight integration still gives you some information to at least partially reduce drift in your inertial navigation outputs. And deep integration is really integration at the signal processing level. And Tom was talking about deep integration. I'll talk about deep integration as well a little bit more in a few minutes. So really, when we're looking at the integration of GNSS and inertial for land vehicles in GNSS challenged environments using consumer-grade sensors, loose integration is not really the best option. Again, this is an example here with some actual data from urban environment. GNSS is going to have, if you're really looking at the position fixes, your GNSS is going to have a lot of outages. So you're going to be costing on the inertial quite a bit. And your performance is going to be limited. When we're looking at the tight and deep integration, it's really not an outage. When you have a 1 or 2 satellites, you still have some information to correct drift in your inertial navigation outputs. So really, for this application, a loose integration is not the right choice. We really need to look at the tight or deep integration approaches. So deep integration, let me take a couple of minutes to describe the deep integration mechanization in a little bit more details, because this is the ultimate integration of two systems, GNSS and inertial. So really, the idea here, we keep all the benefits of the tightly coupled integration approach, but we also use inertial to improve robustness of the GNSS signal tracking And for land applications for GNSS challenged environments, the benefit is we're really looking for tracking of weak GNSS signals, maybe attenuated by buildings or some other obstacles, such as a tree canopy. So really the idea is we're trying to integrate GNSS signals for as long as we can. So there's an incoming signal into your GNSS receiver, you multiply it by the replica, then you correlate the results, and you try to extend this correlation approach for as long as you can. In some cases, you need to worry about the data bit wipe-off. For example, GPSL1, there's a 20 millisecond data bit modulated on the signal. So you need to do something about the data bits, and there are ways to take care of the data bits. You pre-store data bits, or there are some algorithms where you can wipe off data bits without really knowing what's the navigation messages. So we're not really going to go into those details. Really, what I'm trying, the main point what I'm trying to make is what the deep integration is essentially doing is integrating, accumulating GNSS signals for extremely long period of time, as compared to the case of an unaided receiver. So we're talking about 1 second signal accumulation for a deeply integrated system versus generally something like a 20 millisecond integration for an unaided receiver. So again, it's an integration at the signal processing level, and Inertial, where Inertial helps here, when you do this integration, you need to adjust parameters of your replica signal for changes in motion dynamics. So you don't lose energy because of those changes. So this is where the Inertial kicks in and helps the accumulation process. It estimates those changes so the replica signal can be adjusted accordingly. Deep integration, you can use various techniques, various types of signal accumulation. You can accumulate signals coherently or non-coherently. When you apply non-coherent accumulation, you maintain pseudo ranges and Doppler measurements, but you lose carrier phase. And carrier phase, as we'll see in a few minutes, is extremely efficient for integrating, especially with low-cost inertial sensors. So if possible, if you consider deep integration, really implementing coherent signal accumulation and maintaining carrier phase tracking capability for your GNSS receiver is fairly beneficial. So some benefits of the deep integration, again, for land applications, the reason is to recover weak or attenuated GNSS signals. It's extremely beneficial in environments such as tree-covered roads. Here's the example of actual test results and performance of the deeply integrated system under dense tree coverage. So the system is able to recover GNSS signals, in this case GPS signals, attenuated by trees. However, when we're talking about the urban canyon navigation and signals attenuated by buildings, I personally think it's extremely challenging to reliably recover GNSS signals attenuated by buildings. So deep integration in this case probably has fairly limited value. So when we're talking about integration of inertial and GNSS, which GNSS measurements we want to use? There are pseudo ranges and there's a carrier phase. So if we look at the precision of carrier phase versus pseudo ranges, carrier phase really provides you 2 to 3 orders of magnitude in noise reduction as compared to pseudo ranges. The typical noise sigma value for pseudo ranges is at a meter level. When we're looking at the carrier phase, it's sub-centimeter, even millimeter level. And what it buys you when you integrate with low-quality inertials, it really significantly shortens the noise averaging interval. Essentially, it makes inertial errors observable instantaneously to the filter. So you don't really have to apply a lot of noise averaging because the carrier phase measurement is so precise. And the longer averaging interval required for the case where you use pseudo ranges is really not very efficient, especially for very low quality inertial sensors. And the reason why is that because inertial errors are not very stable. They're changing over time fairly quickly. So when you're waiting for your pseudo range noise to average down to the level where you can efficiently apply it for inertial error estimation, those errors are changing. So they may have already changed quite a bit. So it's not a very efficient scheme. Again, the use of carry phase is especially beneficial for integration with low-grade inertial sensors. How to apply carry phase for the low-cost integration? The main challenge there is the integer ambiguity term in carry phase measurements. It's probably not a good idea to try to resolve integer ambiguities in challenging scenarios. When you have, 2, 3 satellites, it's not possible. Even if you have 5, 6 satellites, you need to wait for the ambiguity resolution methods to converge for some time. So when satellites come in and coming out all of the time, resolving integer ambiguities is not really a good idea for GNSS challenged environments, but we still want to use carry phase. Well, luckily, what we can do, we can difference carry phase measurements over time. We're going to lose absolute position information, of course, by doing this difference, but we're going to keep relative position information or position changes. And inertial is really a dead reckoning system, so it doesn't provide you absolute position information. All the information about the aerostate propagation is essentially incorporated in this position change. And of course, when you do temporal differencing of the carry phase, the integer ambiguity term is eliminated. So the measurement quality check is also very important aspect of the system design for land applications in GNSS challenged environments. A multipath, and specifically non-line of sight multipath, can degrade your performance significantly, so you need to do something about it. There's a relatively straightforward approach. You can do RAIM, Receive Autonomous Integrity Monitoring, but the sort of the drawback of the RAIM is that it generally assumes a single failure mode. So in the case where only one satellite channel is affected, it's okay, but with multiple channels affected, it has limitations. So the GNSS INS integrity monitoring is a much more efficient approach. So essentially what you do, you predict what the GNSS measurement should be based on the inertial. You compare it with the actual measurement, and if the difference is beyond a certain threshold, you just don't use this measurement. And when you're working with the carry phase, it's actually fairly efficient, specifically for multipath mitigation and for mitigating or excluding non-line of sight multipath from your solution. Addition of other sensors. GNSS INS integration, I'll show you some test results. Definitely much better than GNSS alone, but still has its limitations. So for land applications, for connected cars, for navigation, and for self-driving cars, if you want to go urban environments and GNSS challenged environments, most likely you will need to add other sensors to the picture. But the good news are that modern cars, they have a lot of navigation-related sensors. They're not there initially for navigation-related purposes, but they can be fairly efficiently utilized for navigation. For example, there's a video camera, radar, odometer. You can use these sensors to improve your performance of your GNSS inertial solution, integrated solution further. Addition of other sensors, the generic integration approach is very similar to the GNSS INS integration. Essentially, you're looking at the complementary filter design, what Tom was describing for his application, and you have a measurement from your aiding sensor, GNSS vision, or something else. You have a prediction of this measurement. You take the difference and you apply it as a measurement observable to your extended Kalman filter. This is the example implementation of the GNSS inertial integration for land vehicles for the car navigation. For the GNSS, it's a GPS plus GLONASS. It's a tight coupling with the use of carrier phase measurements. The INS error model includes 18 states, mostly traditional states, but the position change errors have to be included into the picture as well, because we're working with the temporal phase differences over time. Again, not related to position, but to position change. And again, we're working with errors, not with the actual states. So the dynamic modeling becomes much more simpler, and you can use extended Kalman filter. But we include other sensors into the pictures as well. There's a monocular video camera and also motion constraints. So let me explain you a little bit about the motion constraints. It's not really a sensor, so it comes for free. But for automotive applications, you can assume that in the body frame, your vertical velocity and your cross-track velocity as 0, and incorporate those constraints essentially as additional measurements into the Kalman filter. So let me show you some test results. So we're working on a prototype at this point, and this is an experimental setup was designed by my colleague, Michael Vett. It does include various kinds of sensors, not necessarily low-cost sensors, but low-cost sensors as well. So there's a laser scanner, video cameras, very low-cost consumer-grade inertial, and consumer-grade GNSS receiver. So this is an example test scenario in downtown Tampa, Florida, not necessarily your wildest urban environment, but it has some fairly difficult environments from the navigation perspective. Specifically, there's this underground tunnel and some urban canyons as well in the picture. And we looked at if we look at the GNSS only solution you see on this plot, when we go into denser environments, it doesn't look very good. So when we add in inertial into the picture, it definitely performs much better, especially if you look at its kind of highest scale at the overall solution, but there are still some problem areas. For example, we going out of the tunnel, and there's definitely a very big jump in the solution on the order of probably 20, 30 meters. And looking at this plot here, the solution didn't converge right, so it's really estimating us somewhere in this parking lot here, where we actually drop on the road. So much better than GNSS alone, but still has some limitations. So adding other sensors into the picture, and the solution is basically lane level accurate. So now we stress the system a little bit more and introduce some artificial GNSS outages into the picture to emulate more difficult environments, such as maybe Chicago or Manhattan. And the red line here is essentially artificial GNSS outages. This is the color cordon. And with the integrated system implementation, the lane level position accuracy was still maintained. So in conclusion, just a few takeaway points here. So integration with low-cost inertial sensors really allows simplifying the inertial navigation mechanization error propagation model, but the use of AIDEN data, the proper use of AIDEN data becomes much more critical. You want to use carrier phase, it's most beneficial for mitigating inertial error growth. GNSS inertial still by itself still does not support very accurate navigation capabilities in challenging environments such as urban canyons. But when you augment it with other sensors such as motion constraints and video cameras, then accurate localization becomes possible for all driving scenarios. And that's all I have. Back to you, Demis.
Thank you, Andre. All right, so before we move on to the second Q&A session, a couple of things. First of all, next steps. So a PDF of this presentation will be available at the Inside GNSS website that is given on this slide. And and the session will then, the webinar will also be recorded. And if you have more questions, there's some contact infos for Novotel and Inside GNSS given on this slide. So before we go on to the next Q&A session, let's do one more poll. So Lori, if you could bring up the poll.
Absolutely. And before I do, just wanted to give a quick prelude to it. Defense Secretary Ashton Carter has suggested that advanced technologies such as chip-scale atomic clocks and cold atom systems could lead to, quote, a GPS of things, akin to the Internet of Things, where objects, including our military systems, keep track of their position, orientation, and time from the moment they're created with no need for updates from satellites. So the poll question we have for you today is, do you believe that such systems will eventually eliminate the need for GNSS technology? So yes or no, or probably, probably not, or don't know. Those are your options. So 4% saying yes, 39 saying no, 13 probably, 35 probably not, and 8% don't know. Demos, any thoughts there?
An interesting spread. If they do, then we'll probably have another webinar in the future where we have these technologies fused with inertials. But until then, I guess GNSS will be the choice of integration with inertials. All right, so with that, let's move on to our second Q&A session. And thank you, audience, for sending in lots and lots of questions. We'll try to get to as most of them as we can. So let's go ahead and do that. So the first one is going to be for you, Tom. and it has to do with gravity models. The question is, in the future, as we get more and more precise gravity models, how's that going to change, benefit, make things obsolete or not when it comes to the integration of inertials with GNSS?
So similar to what Andre talked about for certain parameters not being relevant in low-cost applications, for the tactical sensors that I was covering in my presentation, the errors are on the order of millig's for those sensors. So generally for gravity model errors are kind of more on the order of micro-Gs. So certainly for systems that utilize navigation grade sensors like Honeywell QA2000 accelerometers that are accurate to micro-G, with these updated references as they get more accurate, that's going to improve the performance of those systems. So generally right now a aerospace grade navigation system is 0.8 nautical miles per hour for drift, so that might tick that down a little bit for navigation grade sensors. Certainly not for what I talked about though.
All right. Let's see, next question. I guess this one will be for Sheena. And it, well, I guess I'll try to combine two questions because they're similar. Is do the Novatel INS GNSS products include, I guess, RTK integration with GNSS? If not, are there any products on the horizon that would do that, or anything you could say about that?
Absolutely. All of our products actually do have RTK support in all of our span products. So it doesn't matter which receiver or inertial combination that you select, all of them do come standard with RTK support.
Okay. Well, along those lines, I'll try to bring in another question that was asked. Says most of the presentation was on GPS. What about other GNSSs? Is that part? I mean, which ones are supported, and where is that going?
Right. So all of our receivers are future-proof to support GPS, GLONASS, Beidou, Galileo. So that's all been taken into account in even our current OEM6 product line offering. And as more and more satellites come online, we do make sure that all of our products support all of these new satellites that come up.
All right. Let's see. This one is for you, Andre. And it has to do with the initial alignment you were talking about of the automotive applications. You said use velocity and perhaps gravity. The question is, what happens if the car is standing still? Are there other options?
Well, potentially you can use magnetometer, but you really need to be very careful about that because magnetometer can be disturbed. First of all, you need to calibrate for what's called hard iron, the internal magnetic field, but you also have to monitor external magnetic field as well. So if nothing else, maybe using magnetometer, but you really have to wait till you start moving. Then you can do initial alignment in a fairly efficient way.
Okay. All right. Next one. I guess this might be a combined question for Tom and Sheena, but let me start with Tom. It's about integrated, IMU GNSS systems and the specification of bandwidth. What exactly does that mean?
So generally on IMU specifications, bandwidth is the frequency at which the attenuation in the signal is half. So if, say for this question, I see the bandwidth is of the IMU is 330 hertz. That means if you had a sine wave input, your platform undergoes a sine wave that gets fully transferred to your IMU, the output is going to be half the amplitude of the input. And then for IMUs, they lower end, anything below 330 hertz is going to let more than half the signal in, and anything above is going to be attenuated depending on the roll-off of the filters implemented. So yeah, that's generally how bandwidth is specified. There are some exceptions to the half. Some people will specify it other ways.
Okay. So I guess on an integrated, it depends on the inertial use on an integrated INS GNSS product is kind of what that means, correct?
Correct. So
okay.
Just say if it's the minus 3 dB, that's the half, and then there's other ways of specifying it, but it all means the same thing. Around that frequency, your signal starts to get attenuated.
Okay. Let's see, next question. This one is for you, Andre, and it's another ground application. The question was, what specific challenges would a railway-bound vehicle encounter because of the relatively low lateral dynamics? I guess you're losing some dynamics, but you're probably gaining some constraints. Anything you could say?
Yeah, I think
about
it's probably not a challenge, it's a benefit. So your dynamic is much more constrained. So you can incorporate as an additional motion constraint in a manner very similar to what you do with the cars. But with cars, it's when you, for example, you're moving backwards and you're turning, your velocity is not necessarily aligned with the forward axis. So you have to monitor for that. For railway applications, I'm not an expert. I haven't really looked at those applications, but my gut feel is that it becomes easier to implement motion constraints. So probably more like a benefit versus a challenge.
Okay. Let's see, next one, Tom. This one is for you, and it is about temperature effects on IMU errors. How is that accounted for? Are there different ways to account it? How do you deal with that in your mechanization?
So all the specifications that I showed are for temperature compensated IMUs. However, for MEMS sensors, even tactical grade, there's still drifts that are remaining proportional to temperature that are simply non-deterministic or non-repeatability. So modeling them in the Kalman filter as temperature dependent is certainly one option, depending on your sensors and depending on how much they drift. So the repeatable part is taken out by the calibration if your sensor has calibration, and the residual can be modeled proportional to temperature, since what you're modeling in your Kalman filter is statistical in nature, and so is the non-repeatability of the sensors over temperature that are remaining. So it's a good fit, and it's very critical to model that correctly.
Okay. Let's see. Next one. I guess I'll pitch on at you, Tom, and then at Sheena, and it is about deep integration and software-defined receivers. How much can a software-defined, how easy would it be to do something like UTC on a software-defined receiver? Any thoughts on that, or comments on that?
I'm by no means an expert in software-defined receivers. I haven't worked with them, but it's something that you can completely define and control. So it's a tool that kind of fits into your lab environment. And again, I would caution that that the timing of the system is really critical in UTC, and also that if you make sure that your software-defined receiver is going to match up with the final implementation, if you define a receiver in software that doesn't match up with what you're going to use in hardware, it could be disastrous, of course. But if you're using it to help you define to design the receiver, and you're modeling the IMU errors appropriately, it would seem to be a very good thing for a UTC design.
Right. Andre, you want to add anything to that?
It's definitely not an easy thing to do. In Novotel, we have the luxury of having our tracking team and our inertial team on the same building, so we have control over all the algorithms that goes on within the receiver, so we're able to do this ultra-tightly coupled integration. But without an intimate knowledge of both pieces of technology, it could be disastrous if you don't do it right.
Yeah, I agree with that. Basically, the benefit of the software-defined receiver is that you have a complete control over the receiver design, so you're not limited by anything. But it's not an easy thing to do. So basically, you have to know very well the receiver part and the inertial part. So essentially, you have to implement both.
Okay. Let's see. Next question is going to be for you, Andre, and I guess both Sheena and Tom could pipe in too if you want to add to this. But do you think it's going to be cost-effective to do a deeply integration on a cell phone type of a device with the low-cost sensors that you find in that kind of an application?
If you're looking at the deep integration for carrier phase, then no. because there's inertial, and inertial sensors are getting there in terms of the quality versus cost. But there's another component, which is clock. And clock needs to be fairly stable as well if you're looking at the coherent integration. So the clocks are not there yet. We're looking at the chip scale atomic clocks or oven-controlled clocks. They are in the range from $500 to probably $2,000. So obviously that's not efficient for a cell phone type of application. If you're looking at non-coherent type of accumulation schemes and with narrow bandwidth code such as CA code, then I don't really see a lot of value using inertial for aiding of GNSS signal accumulation. So the deep integration for cell phones, at this point I don't see a lot of value. Again, the clock is an issue for carrier phase type coherent integration, and there's not much benefit from dynamic aiding for non-coherent code phase type of accumulation.
Thanks, Andre. Tom or Sheena, anything you want to add to that?
No, I think Andre covered it.
All right, great. Let's see. Next question. Which one should I? Well, let me ask you, because I think you talked about it briefly, Tom. So I'll direct this one at you. Are there any effects on IMUs that are due to aging? And if so, are they big, major? Can you say about them?
So yes, I mean aging does impact IMUs. There's a few effects on MEMS. A lot of the error sources are due to stresses in the actual structure of the MEMS itself. So some of those stresses may be relieved or may be changed as the IMU ages. At Honeywell we specify all our IMUs aged out 20 years. So 20-year life storage. So it's really end of life specs that you'll see in any Honeywell specification tables, and that's fairly typical for tactical IMUs, but not for consumer, lower, and even some tactical companies don't do that. So yes, aging is a major concern, and it is something that as you get to applications where you're looking for higher performance, you want to know how it's going to perform at the end of its life. So that's really, really critical.
Okay. Let's see. I mean, maybe this is a dumb question, but I'll ask it anyway. That's my own question. That was motivated by that. Is there something equivalent on the GPS receiver side, or, are all the components? Maybe a question for Sheena. Is there something equivalent to aging on the receiver side?
No, there really isn't. It's not as susceptible to performance degrade as an inertial sensor. So no, we don't really have those challenges in the receiver side.
Okay. Let's see. This question is for you, Andre, and it has to do with deep integration. And it's basically the question is with deep integration in extended signal accumulation. Are you really, in effect, aren't you doing some delaying of the measurements? And what's the effect of this on the final navigation solution?
You're not delaying the measurements, you're decreasing the sampling rate. So in other words, if you're looking at the unaided receiver, you can output the measurements practically at 50 hertz or even 100 hertz. If you're doing deep integration at 1 second, then you can only output measurements at 1 hertz. So, if you're looking at the high dynamic applications, then 1 hertz is probably not enough. But you can use inertial for providing you, higher rate outputs in between those 1 hertz measurements. So again, you're not really delaying measurements, you decreasing the sampling rate, which you can fairly efficiently overcome using inertial.
Okay. Do you want anything to add to that, Tom?
No, I think that was a good answer. That's sufficient there.
Okay. All right. So it looks like we're coming to the end of our session here. So maybe we could put in one more question here, and let's see. And I could pitch this one to I guess any one of you, but I'll start with you, Tom. Consistency of Kalman filters. Is it something you do? It's checks you have to perform to make that?
Yes. Andre touched on it briefly with the measurement rejection. That's certainly one method of looking at it. The other thing is measurement noise considerations. If your noise agrees, you generally look at the normalized residuals and make sure over whatever period you have that they're RMSing to around 1. So normalized residuals are really the difference between the measurement and your prediction of the measurement normalized by your covariance. So it's accounting for all parts of the common filter, and you're making sure that they're in agreement. The other thing you can do, and that's done more in high integrity applications, is to run multiple common filters excluding certain measurements or pairs of measurements. And you can think of it as kind of a RAIM for an integrated INS GPS application. It's called solution separation, and it's done in some of Honeywell's really high-end commercial products, but similar things could certainly be applied on the low end to ensure KF common filter consistency.
All right. Well, we have a lot more questions, but not enough time. So thank you very much to the audience for joining us and for asking all those questions. And with that, I think I'll hand it over to you, Lori.
Okay, thanks so much, Demos. And before we sign off, I'd like to thank each of you for joining and trust that you found today's presentations to be of value. Special thanks to Tom Jekyll and Andrei Soloviev, and of course our sponsor and co-host Novotel and Inside GNSS. Also special thanks to our logistics producer Patty Van Hooser for her behind-the-scenes collaboration and support. Most importantly, thanks again for joining. This is Lori Dearman saying, hope we see you on the next one. Have a great rest of the day.